Hello, everyone. Welcome to our AP Statistics final presentation, where we will be comparing NHL games played versus points scored throughout the season. And this is presented by Max Knight.
Aiden Karamati.
Andreas Galanis.
All right.
All right. Research question. Does the number of games played by an NHL player, RGP, affect the total points, PTS, scored by an NHL player? Why hockey? Our group contains a hockey fan, Aiden here, and some passive observers, me and Max. Aiden wouldn't stop talking about hockey and using hockey data because it gave us an excuse to watch some NHL fights. In analyzing data on individual hockey players, we saw some players had massive amounts of games played with very little scoring. And alternatively, some players had few games played and massive scoring. We decided on analyzing the correlation between games played and the points scored to see if this can provide insights into player performance and the impact of playing time. So, first step, gotta state it. Our null hypothesis. There is no correlation between the number of games played and the total points scored by NHL players. Our alternative hypothesis. There is positive correlation between the number of games played and the total points scored by NHL players. And we're using an alpha value of 0.05. So for our data collection, we had our data source from that included player statistics and specifically columns for ranks, players, games played, and points, and the website's listed there. Population is that every NHL player in the 2023 to 2024 season, which is around 924 players, and our sample is 30 randomly selected players from the population. Our independent variable is the games played, dependent points scored. Bias reduction, we did simple random sampling from the total population and a standardized process for data collection, minimize variability, and confounding.
So here's our plan. Since we're using two means, we're going to use a lin-reg t-test. And we're going to go over it later, but we're going to need simple random sampling, a sample size of greater than 30 for the central limit theorem. And since we're choosing 30, it's less than 10% of the population of 924 players. And we'll hit all three later. And Andrew will explain how we're going to do the SRS.
So for SRS collection, our first step was each player was assigned a random number by ranking 1 through 924. Second step, we used the ran-in no repetition function on our calculator for numbers 1 through 924, and we did and for 30 numbers, and we see our results right there. Third step, record games played and total season points per random player corresponding to their ranking. You can see those numbers listed right there. Here's our sample data with everything listed in clearly. And our summary statistics for each of this. So for our means, the games played was 43.67, points scored 16.4, median was 44 for games played, median for points scored was 11.5, mode 1 for each of them. Standard deviation for games played was 30.58, points scored was 16.90, and the variance for games played was 935.13, and the points scored was 285.56.
Let's look at some graphs, and we'll continue to analyze the graphs from here on out. So first, we built to help visualize the lin-reg t-test, we built a scatter plot and then drew the line of best fit with the green line. And on the x-axis, you see we have games played, y-axis we have the points scored, and let's see. I'm going to explain the numbers in the equation that we got. So the slope, which is 0.448, it represents a positive correlation between games played and points scored. And let's see, for each additional game played, the predicted total points scored by each player would increase by 0.448. In addition, the y-intercept of negative 3.0223 represents if a randomly selected hockey player played 0 games, he would score a total of negative 3.0223 points. Here we can see that we have 2 outliers in the data as well. And to find this, we drew a linear regression line, 2 standard deviations above the green one we have there. And as you can see, we have 2 ones there at around 48 games played and around 82 games played. And here, let's take a look at our residual graphs. The strength of 0.0805, it means that we have a very strong linear regression line, and it shows that there's a positive correlation between the two. The form, because there's no pattern in the residual graph, we can say that there is a linear correlation between the two variables. And finally, the R squared data, the R squared number of 0.0648 represents that 64.8% of the variation in the total points scored is explained in the model that relates points scored to games played. So here's our conclusion. The inference procedure we chose was a linear regression t-test. We put that in our TI 84s. The t-value we got was 7.177, and you can find you can use that to find the to test your hypothesis by using the TCDF. But in our case, we use the p-value, which equals 8.23 e to the negative 8, which is a very small number, way less than 0. And here's our conclusion. Since p is e to the negative 23 e to the negative 8 is less than alpha of 0.05, we reject the null hypothesis. There is a correlation between games played and total points scored by hockey players. And let's discuss the two different types of errors. Type 1, we reject the null hypothesis when stating that there is a correlation, even though the null was actually true. And in type 2, we accept the null hypothesis, but in reality, there is a correlation. Here's some limitations from our hypothesis and our test. Because we're limited to quantitative variables, the points in games played, we lacked qualitative variables such as like the player's position, which could have played a major role into how many points they would have scored, as a defender would likely score less points than a forward. And we could improve our analysis and our data collection by looking at the total population and trying to find the true values from our experiment. So we actually did that, and we're going to be comparing the true data to the sample data with Aiden.
So we can see in these summary statistics that there's clearly a big difference between the true data and the sample data. So our mean, median, the standard deviation variance for the true data is much greater than the sample data. And this is because with the sample data, we limit ourselves to a population that's 31 times less than the true population. So it's a good metric that we can use reliably for an inference, but you're never going to beat the actual the true data from the full population. And we can see that on the following graph, the scatter plot with the outliers are in red. Just to note, the graph, most of the points are at or below 82 for games played. This is because there's only 82 games in a regular hockey season per team. So all of the points to the right of 82 are from players who were traded between teams, and so they ended up playing more than the regular 82. And there's 1,300 games just about per season, and so that's how they exceeded that threshold. But we can see our p-value is 2.46 e to the negative 112. So it's a very small number. So once again, we can reject the null hypothesis. It's statistically significant. And then comparing it to the graph on the other side, we can just see the amount of data points that we're losing by using the sample rather than the full data set. And if you want to look at the residual graphs on the following slide, we can see the difference. So the strength for the full data is an R of 0.697. So the correlation between the variables is weaker than that of our sample, but it's still moderately strong positive correlation. There's a strong left skew to the graph because of the nature of 82 games being the typical limit, which can be exceeded by trading, but that's the exception to the rule. It's not the rule. And then for our R squared, 48.6% of variation in the total point scored is explained in the model that relates to the point scored to games played, as compared to the 64.8% of the simple random sample that we can view on the next slide. And there are more outliers, so the outliers are weaker. And also just comparing it to the 0.805 for the R, you can see that there's a weaker correlation with using the full data set. Thank you.
Thank you.